Hello everyone and welcome back to part 5 of our PyTorch series. So far we have learned tensors, we have learned the neural networks, training loops, optimizers, devices and broadcasting, and in our last video we learned about datasets and data loaders. Today we're actually answering the big question, how do we actually use a trained model? So in this video we will cover the inference, we will cover the evaluation mode, and at the end we'll also cover saving and loading our models, which are really important in machine learning. So if you guys are ready, let's go ahead and begin. So we can just head over to the project we've been working on in the last videos and just open a new line of code. It's just the same project, nothing new. And before we switch to the evaluation, I want to discuss what the evaluation actually means. So when training, the PyTorch will behave differently. For example, it will consider the dropout, that it's active, and the batch normalization, it will behave differently, and even the gradients are tracked. But when we use a model, we want a stable behavior. And this is where we will use the evaluation mode to give a stable behavior for the model. So in order to switch to evaluation mode, we can type out model.eval. So this model.eval basically tells PyTorch that the training is over and we only want predictions. No randomness, no weight updates, just predictions. And this does not change the model's weights, by the way. It only changes how the model's behavior, how the model behaves internally. And next, we can also disable the gradient tracking, as we just said. For example, all we have to do is write out with, so it would be a loop, with torch dot no grad. So basically, before we use this, I want to explain what this line does. Basically, it disables the gradients and it keeps the gradients that are only needed for training. Because if we track them each time, we use up resources, we use up memory, and it's wasted usually. So this can slow things down as well. So to be faster and more efficient, we can just use torch.nograd, and this will basically tell PyTorch that we only want predictions and it shouldn't actually calculate the gradient itself. And this part in itself is critical for inference. So now let's run a small inference. So just continuing on this code. So as I said, this was a loop. So we'll use with torch no grad predictions equals model, and we'll use x. Okay, let's delete that. Okay, so first the model.eval, it will switch the model into evaluation mode, and the torch no grad, it will disable the gradient tracking, and inside the loop we will pass the input data x into the model, and this is what we call inference, where we use a trained model to make predictions. And if you can notice, it looks kind of similar to the training loop we did, but without loss or backward or optimizer steps, basically like this. Much more simpler and more efficient. And we can use this to further expand, similar to the training loop. So we will use the same data set we used in our previous video, which will be the X batch and Y batch. So we can set the total loss to 0, and this will keep getting updated. So now we make a loop for X batch, Y batch in data loader. Predictions equals model X batch total loss plus equals criterion, and we will use pred and Y batch. Okay, so prediction against the Y batch. And we can set that to item. And finally, we can just print this. So let's go ahead and print, let's say, eval loss for evaluation. total loss divided by the length of the data loader. Okay. And now we can also add the inference on a single input. So let's say new x equals torch.tensor 5. Output will be model new x, and now we print it. Prediction for 5 out. Wait, it should actually be out.item. And so now just to explain quickly over the code we have just written. So model.eval, obviously we used it to enter the evaluation mode. So that means we are done training and now we want the model to start evaluating. Then we use torch.nograd with torch.nograd. That means that during training, the model should not pay attention. It should not track these gradients because they are useless. They should only be used during the training. However, the gradients in the evaluation or inference phase, they are completely useless. So it's more efficient to just not track them. So basically you just disable them with this command, and this will make our inference faster and even more memory efficient. Then we use the total loss equals 0, so we just initialize the loss just to keep track of how wrong the model is. And at the end we'll just sum up over all the losses. And then we have the 4x and y batch in data loader. We just loop through our dataset using the data loader. And if you remember from part 4 in our video, x batch is the batch that contains the inputs, and the y batch is the set of correct answers. So for every x batch input, there should be a correct y batch output. And also for the predictions equals model x batch. So this just runs a forward pass, and we give the inputs to the model, and the model produces the predictions, just similar to what we did in the last video. Then we calculate the total loss. So criterion is our loss function. So it will actually, if we want to get technical, it will just be the mean squared error. And the .item command, it will convert the loss tensor into a regular Python number. So when we get the output, it will just be in a number, not just in a bracket. It will just give us a number. And we add it to the total loss so we can compute the average later. Then finally, we print the average evaluation loss, and this number will tell us how well the model performs on the data it wasn't actively training on. And the lower we get is the better. So we can also go ahead and print this now. And as you can see, for the output, we got 0.04. And this actually means that our model learned the relationship pretty well. And similarly, if we continue on the code, the second paragraph or block of code is the inference on the new data. So this is actually a real world use case because we create a brand new input that the model has never seen before. So the double brackets basically here means that the batch size is 1 and it only has one feature. That's what the double brackets mean. And to run the inference, we will use the out equals model new x. So basically we just pass the input into the model, and this is what's called the inference. So we're not going to be training it, no loss. It will just make a prediction. So, and after we print it, we see that the number we got is actually pretty close, which is, if we scroll down, it's 9.64. And if you followed on our last video, we set the rule of the output to y equals 2x. So basically, for every x input, we need the y to double the x input. So we were training it here, for example, in 5, and it gave us the value of 9.64, which is pretty close. So it shows that the model can correctly predict something very close to 10. And this is actually how a trained model is used in practice. We give it a number it has never seen before, for example 5 here, because if you want, I'll scroll up to our list, which we had. This was the data sets we used. So the inputs we trained the model with were 1, 2, 3, and 4, and the outputs 2, 4, 6, 8. There's no 5, there's no 10. And using it for the first time, we can see that it can correctly follow the rule to an extent. So 9.64, very close to 10. It shows the model has correctly learned the process. And notice how this loop we just did looks similar to the training loop we did in the last video. But here we don't use the loss, we don't use backward, we don't use optimizer steps. So it's much more simpler. Alright, so now that we have trained our model, evaluated it, and even made the predictions, there's a big problem. If we were to close our device right now, everything would be gone pretty much. So we would have to run the code again to make the same training, same predictions. So we need to teach the model again, basically. And so we need to now learn how to actually save our model and later load it back, exactly like the real machine learning projects do. So this is what I want to show you guys right now. So we can go ahead and type out torch.save model.state dict model.pth. Then we can print out, I'll explain this all in a second. So we can say OK, saved, wait to model.pth. So the model state dict, this contains all the learned parameters of the model, which can be the weights, the biases, and just everything the model has learned during the training. However, it does not include the training loop or the optimizer. It just includes we can say the brain of the model. And once we use the torch.save, we write the data of the model to the disk. So we are saving the model's weights into a file called model.pth. And the pth means the PyTorch file extension. It's the standard PyTorch file extension. And finally, we just print the confirmation, so we know that the saving has worked. And a quick tip would be to only save the weights, not fully the model, not the full model object, because the code can change and the weights can stay compatible. So this gives you the flexibility and helps you avoid bugs later. If the code changes, you'll have an issue. However, the weights always stay compatible, so it's an easier option and the more, how do we say, the preferable option to save the weights instead and not just the full model. So now that we have saved our model, now let's go ahead into loading the model. So we can open a fresh instance and say loaded model equals my model. So we just create a brand new model instance. The model, it will have the same architecture, but no training yet. And it will also start with random weights. So we can load the weights now. So loaded model dot load state dict torch. We can say torch.load and the path model.pth. Okay, so here we just load the saved weights from the disk. So earlier we just saved it, and torch.load basically reads the file that we have saved in. Load state dict, it will import these weights into the new model, and at this point, once we have done this, the new model will become identical to the trained one. so we would not have to train the new model again. And similarly, we will put the loaded model into evaluation mode as well. So we go over here, just do loaded model dot eval. So just like before, we just switch to evaluation mode so we can get the correct behavior for inference later on. Then we can also just print the confirmation. Wait, let's say okay, loaded weights into new model instance. Okay, so this would just give us the confirmation that the model is fully restored. And next we will use the inference after loading. So basically, let's go ahead and type it out. So we can say with torch dot nograd new x equals torch dot tensor 5 output equals loaded model new x print, let's say prediction after loading, and it will, let's say for 5, so it's the same input as we used earlier, and we put out.item so to get the number. So after we disable the gradients, because we're only doing inference, we will test the same input we used earlier here. So it will let us verify that the loading worked correctly. And the output, we just pass it the input through the loaded model. So just a prediction again, no training done here. And finally, we print the prediction. So the error we get here is because the my model is not defined. So simply to fix this, we need to just define a simple my model class, and we can quickly do this. So if you go over to here, class, let's say my model, we put nn.module inside, then we define init self super dot init self dot linear equals nn dot linear. We will say 1 and 1, so 1 input and 1 output. And yes, we also have to import the nn library, torch dot nn as nn. Now it should be defined. And now we just define the forward. Define forward. Let's put a space. Self x. Return self.linear x. So we have covered this in our previous videos, and we just needed to do it here as it's essential so we can run the code properly. So now we can run it again. So once we run this, we can see that we got 9.6 as well here for the loaded model. And if we scroll up, we can see that for the previous run, we also got 9.6. So this actually proves something important. It shows that even after saving, closing, the model still remembers what it learned. That's why saving and loading is a really important concept, especially in machine learning. And this is basically how the real AI system works. Models are trained once, then they are saved to the disk and loaded later for websites, mobile apps, APIs, basically everything. Because the training is actually really expensive, however, the inference is cheap. So training should be done as low as possible, and just based on that one training, you can compute multiple models at the same time using the saving, loading, and inference. And that basically wraps up today's video. So we learned how to do the evaluation and inference for models. We learned the saving and loading for models, which are both really important for machine learning and neural networks. So from here on, we are ready to move into more complicated and more advanced models. So if you enjoyed this series so far and found this video helpful, please make sure to like and subscribe, and I'll see you guys in the next one.